Okay, so I understand that the way that, you know, for professors, it's always complicated to quiet down students so that they start listening, mostly so they stop disturbing each other, and it's also a little distracting for us. So it was always a puzzle. So, you know, I watched Dan Garcia, and his algorithm was, whoa! Okay, so I stole that. I used to have an algorithm when I taught algorithms last, and the algorithm was to do some sort of little, to shh you guys. But I did it with graphics. So I'll show you one of my graphics from a few years ago, and you can tell me what you like it. I was chatting with Chiesa, noticed the slides and said it was kind of funny the way I did it, so I'll show you the way I did it. What else? He says he goes shh until you can be quiet too, so that's cute. Okay. 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 Well, I'm going to quiet you down. Okay. Okay, so I make it topical. So what is this? It's both 3-sat and vertex cover because they're the same problem, right? So either one works. Okay, so this is like the clause with S or H or H. You should actually have different literals, but that's okay. H or not H, and a lot of not H, I don't know what that means and what sound that makes, but okay, so, and then dot, dot, dot. So now if you assign S to true, this S, that H to true, and one of the dots to true, and you have to assign the last dot to true. And then you get both, you see that it's a true, it satisfies this assignment, this 3-sat formula, and it's also the independent set of the graph I showed you at the beginning. Okay, so I don't know. Man, it is painful to get such animations to work. You know, hours. You know, the size is 4. Okay. Okay, why do I do slides? Okay, so we had the mid-semester survey and I read everything. So thank you, I guess. I usually have to have a bottle of liquor, very hard liquor. I thought about bringing the bottle of liquor here and reading a couple of comments with you, but I thought that would not be appropriate. So, okay, but why slides? Okay, Sinho. Who knows Sinho? Who's heard of Sinho? Yeah, okay, Sinho is he's a former student, you know, a very, very accomplished student. So I no longer use the word smart because I don't think it means anything and has any value. Mostly. Okay, but he's very accomplished and serious, okay? This is over email. Things are good. My daughter tells me, you're not supposed to put text up. You're supposed to take a screenshot of the interchange. And I was, okay. Okay, so I don't do this correctly, but okay, sorry. So things are good. I'm co-teaching 170 and teaching 375. And I put 375 on there for a reason. 375 is the pedagogy course where I teach people about pedagogy. I teach them about the research in student learning. So, and I've done a lot of reading on student learning. So when I say things about student learning, it's not just from 20 years of experience, which counts, but it's also from looking at the literature, okay? So, and I'll show you some if you want. If you guys want, during the breaks in the future, I'll show you some cool things about student learning. And it might help you in your own learning process. Okay? It's fine. Many kids don't like slides. I think I have to tell you why I use them, because I don't want you upset. I mean, like, student learning is complicated. And I don't think frustrated or struggling or any of those things are a problem. But angry starts to cross into a problem. And there's some anger in that survey. Oh. I think one said, "Why are you so stubborn? Why do you use slides? Why are you so stubborn? Stop being stubborn." I should have brought the liquor, yeah. All right, okay, so I use them mostly I use them because I think it's good for you. I think it's the best way for me to communicate what I know to you. And apparently he doesn't agree, which is fine. I'm surprised that they are so, okay, so this I didn't engineer this, but he said this, okay. In a subject like algorithms, I feel that a lot of arguments are demonstrated well by examples or verbal explanations, but painful to write down, which seems ideal for slides. Yeah, I think that's part of it, and something like that is what I would have said, but he said it better because he's, as I said, a very accomplished student, and so, okay, but let me tell you a couple of other things. I could speak, I don't need to speak only through Sinho. I really thought about this. People like watching math be presenting on boards. A lot of people do. And I've looked at the literature. There's no evidence that it helps. Okay, if there was, I would do that. I mean, I really would. If it was like clear to me that it helped, I'd write on the board. But there's none. I've looked and looked and looked, and there's lots of it, not particularly any evidence about that. So that's one reason. And when I watch myself on video, I'm like, why am I taking so long to write that down? Okay, and even when I watch Chiesa, who is a brilliant lecturer, for me, it's noise to see him write things down. You know, I can't tell when he's talking to me. When he's looking at me, I can tell I should turn up the volume or slow it down or something, whatever you guys do. And other times I'm like, okay, what is he doing, right? So for me, writing on the board, watching writing on the board, and then I looked at the literature and it doesn't seem to make any difference, okay? The other reason the slides are important, and this is why I really want to tell you this, is that you have them, okay? They're there, they're an artifact. You can see me explain them to you, or you can try to recover the material yourself from them. And the slides are extremely aligned with the book. I believe all the information you have should be saying the same thing, perhaps in different ways, okay? And I don't like this notion of looking at that source and that source and that source, which we all do with internet, right? We look up, we surf internet. Whenever we don't understand something, we're looking at Wikipedia pages and blah, blah, blah. Whenever I read Terry Tao's blog, I'm constantly looking at Wikipedia pages, right? I don't even understand most of the words, whether they're verbs or nouns. So I understand, but here the material is not like that. It tells you what it's all self-contained. And the slides are just trying to support that. So you can use the slides to guide you through the experience. I think the book is great. If you can learn from the book, great. That's absolutely wonderful. I think everything's in the book, okay? But the handout version, the handout version you can glance at, sort of see what's going on. If you have a focus, you get an outline of what's going on, that's fine. I think what I do with the slides, every time I unfold, sometimes it's for a joke or just to give you a pause, but sometimes it's like there's an idea there, and you should try to prove it to yourself. And even some of the people complain, he doesn't seem familiar with the slides. I am. I'm just sort of pointing out when I slow down, okay, this is something that requires some thought. It requires some thought both in whether it's true, how it's true, and how you're going to process it. And all of those things are things you can do if you go step by step through the slides. If you do that, you might do well. I never say this, because was my intention in making the slides, but I'm a little self-conscious, so I didn't say it. But one of the students came to me and said, hey, I did this on his own. And he said, hey, I just went through the slides step by step, making sure I understood it, did great on the midterm. And I also felt like I really understood the material. Now, to be sure, you can do that with the book. I think the book is better. It's really well written. The problem with the book is it's a book, okay? It's hard for us to give the level of focus we need to one sentence to really focus on that. And the unfolding is all I'm doing here. I'm taking those concepts, I'm unfolding it and say, this is a sentence you should pay attention to and really fully understand, Okay? That's the point of it. Okay? Here's some specific comments. Just, I mean, these are summaries. I'm not going to give you specific without a lot of beer. So he just reads from the slides. He goes too fast. That's a contradiction. There's not that many words on the slide, right? And it is a contradiction. I went back and looked at the videos. He just reads from the slides is not true. He goes too fast. I got to say, it's painful for me to watch myself at regular. Who watches me at double speed? Right? Does anybody watch me at regular speed? Oh, you do? Okay, well, there's somebody. Okay, good. Okay, so for me, it doesn't seem too fast, but there's a lot. I mean, it doesn't seem fast, but it seems like there's a lot. I admit that there's a lot because, you know, with slides, it's easier to present more. And more to me is, you know, I'm backing out at different levels, or at least I'm trying. Okay, there's an overview, there's connections. When I did Huffman coding, I was able to have the time to connect it back to this notion of a greedy choice in greedies and this sort of optimal exchange property in the MST and give those connections. I'm an algorithms guy. I've been an algorithms guy for 30 years. So I do sort of know how to approach this. So I try to throw in how I approach these things. I tell you jokes. My jokes are hilarious. Well, okay, so I tell you jokes for a reason. Because it's a bit fast. Focusing for that long is hard. That is true. That's something you see in the education literature. The jokes are a break. Then there's a problem with the telling jokes. One kid who does very well, like in the class, he's like, I don't understand your jokes. You know, and he was very sincere. He was a very sincere student, and he felt he should sincerely understand my jokes. And I was like, that's not important, right? You know, it's okay. You know, you don't have to understand the jokes. It's really for a break. That's all it's for. Okay, and the details. Of course, I have to tell you the details. And the details here are like not calculations. These are arguments, right? It's like, how do you get the argument in the right shape? Okay, to make it prove the thing you want. We have gone to a higher sort of, a different level of mathematics where you're making arguments. So the details are not like, oh, that's just the details. The details can be is what you're working on learning, how to manipulate those into arguments. Okay? And finally, the risk is you're going to be frustrated. Look at all the things I'm trying to communicate in one lecture. It's a lot of stuff. Nobody gets it. It's fine. It really is fine. There's many levels to Grok. I'm just putting it out there. It's one pass. It's some feeling of what's going on, okay? And maybe you get some things, maybe you don't. Okay. Okay, so today we're going to do some more reductions and dealing with NP, coping with NP completeness is the chapter. This coping with NP completeness. To me, it's there's only one thing in that whole coping that I really like, which is approximation algorithms, which is what I do. But this coping with it is what you're going to be doing with your project. So it's actually very, the reason I don't like it that much is you can't prove much about it. They're just sort of heuristic or exponential. So neither of those do I. I mean, I like them fine. They work fine. There's not much to say about them. It's not really the content of the course. We try to prove things. So in the coping, there's very little proving, okay? But we're going to do that. Okay, so this is a reduction. Does everybody recognize this? So you have an instance. You have some way of translating. You have a search problem A and B. Now an algorithm for A, what this is saying is you use a subroutine algorithm for B. It's not any more complicated than using a subroutine, right? That's really all you're saying. That's what a reduction is. It's saying I can use a subroutine for algorithm B for algorithm A. Okay? And what does that mean? That means if I have an input for algorithm A, I can translate it using this function from an instance, the input or instance of algorithm A. I can translate it using a function into an instance of an input, a valid input for the subroutine or algorithm for B. And now B answers two things. It either gives us a solution, which is this, the solution of the instance, the input it got handed, And then you do is you translate that solution back to a solution for the input for algorithm A. Okay? If not, it could also answer there's no solution. And if it answers no, what should be the case is there is no solution to this instance I. Okay? It's just a subroutine. Okay? It's really sort of subtle and complicated, and people do the reductions the wrong way on the test every day. When we're grading the test, oh, wrong way, 0, wrong way, 0, wrong way, 0, right? So be careful what you reduce from what, okay? And so what we're saying is if you have this structure, which problem is harder? B, okay, that's the wrong, if B is easy, then what do we know about A? Yeah, assuming this function is efficiently computable, this instance, and this function, the solution coming back is efficiently computable. Okay? So if A is hard to solve, what do we know about B? Yeah. Okay, so this says A goes, A is reduced to B. Okay? And B is reduced to C. Now, does that tell you, can you reduce A to C? Yeah, you just replace this box with another box that looks the same, where you replace where you have A with B and where you have C with B with C, right? It's all fine, okay? C is at least as hard as A. Okay, any search problem, even me, when I look at this, I'm like, is that the right direction? B is harder than A, C is harder than B, so C, yeah, right, right? Okay, so any search problem can be reduced to B, then B is NP complete. Okay, so that's what NP completeness means. Okay, you've already done this with Professor Chiesa, and I had to have my Italian lesson because I used to call him Professor Chiesa, but he was very polite until I asked him one day, and he said Chiesa. And I was like, oh, I'm sorry. Okay. Okay, so this means that B is at least as hard as any search problem. And remember, the way the book defines search problem is this class NP, if you look on Wikipedia. But the search problem is a phrasing they use in the book. And it says any search problem is a problem whose answer you can confirm in polynomial time. So any problem in NP. Okay? Okay, so the search problem in NP is the same thing. Okay, so let's do one more reduction. One more reduction? Yeah, I'm going to do one more reduction. Okay, so just have to look at the time. I left my phone in my car. Okay, so okay, set of compatible triples. These are boys, girls, and pets. That's what they are, and B is a number. Okay, so these triples are this boy and this girl and this pet are all compatible, right? It's a dachshund and a boy and girl who like each other and are both okay with the dachshund. Who would be okay with the dachshund? I don't know, but here's an example. Or I guess these pets are not even okay. So these are two kinds of pets, not a dachshund. Okay, so there's Bob, Al, and Chet. Now a triple, I'm going to denote a triple with this triangle. Okay, this triangle says Maria is okay with Al, and they're both okay with the cat. Okay, that's how I do. Is that clear? And we could have a bunch more. This triangle, there's a triangle that connects Al and Kathy and cat. So Al and Kathy would be happy together with a cat. You know, it has a lot of applications, but this is a silly one. Okay, so we want to reduce from a 3-sat formula. We want to show this problem is hard. Remember, this is very similar to matching, right? Remember bipartite matching? You had boys and girls, and you were trying to match the compatible pair to maximize the number of pairs that are, boys and girls are probably not the best example. It's jobs and people. And you can match people to jobs if they're compatible and try to get as many people jobs as possible. Okay? Okay, so what I want to do is show when we've gone from bipartite matching to essentially tripartite matching, or 3D matching, things get much more difficult. It's NP complete. We don't know how to solve it. We think it's going to take a long time. Okay, so Boolean variables. So that's a Boolean variable. Do you see how? Okay, well, so let's just think. There's some boys, and there's some girls, and there's some pets. Okay? So, and there's some triples. Okay, so this triple up here has P1 connected to boy 0 and girl 0. Okay? And there's P2. So now, if I chose that triple there at the top, could I choose any of these triples that are, let's call them the vertical triples. If I choose the top vertical triple, what other triple can I choose? Only the bottom one. Okay? If I choose the left triple, what's the only other triple I can choose? The right triple. Okay, so isn't that a variable? It's a binary variable, right? Once I choose one of the triples, it's like either I'm vertical or horizontal. Right? That's the choice. It's a binary variable. It's a Boolean variable. Right? Okay. So it's called the gadget. When we say variable, there's these gadgets. You've seen them before with the vertex cover or independent set. He used independent set, I believe. Okay. So either these are the triples you choose, the horizontal triple, which we're going to call false. We're just going to assign a meaning to them. Now, notice that if you do this, you have two pets that are free. Okay, in the false case, you have the odd pets here are free. Okay, they're available to be matched to other pairs. Okay, so this gadget, what it does is it constrains you by saying, okay, if I'm going to assign this gadget false or this variable false, I'm going to make these two pets free. Go Lassie, be free. Okay, so the other way, the even triples, the even pets are free. Okay? Okay. Okay, so let's say you have a clause, X, not Y, and Z. And a boy, what we're going to do for the clause is we're going to build a clause gadget. Okay? And what we're going to do is we're going to make, for the clause gadget, a boy for that clause and a girl for that clause. Okay? And now the truth of it is going to be made available by which pet they use. Okay, so we're going to make it so that these are the triples that involve this boy and this girl. So all these things are the same in all these triples. Okay? So what they're saying is here, what we'd like for this clause to be true is to say that one of these variables is true. Okay? So if one of these variables is true, I should have a variable gadget where there's a pet. If this variable gadget had a true assigned to it, the even pets would be free. They would be free to go join this clause. Okay? And so we put in something for this pet, pet 0, and pet 2, because if this boy and girl grab a pet, they're happy. Okay, we're trying to satisfy all these pairs. Okay? And similarly for Y, if Y is assigned false, remember that the odd pets are free. So we make clauses that say this boy and this girl are happy with an odd pet from Y. Okay? And that's the same, and similarly for Z. That's again an even pet. Okay, so there's 6 triples. So now what I've described is this F of I. I've translated from a formula to an instance of 3D matching. Okay, for each variable I build this gadget, and for each one I'm going to have 2 free pets, whether it's true or false, so I can use the variable in 2 clauses. Okay, or I can use I can even use it in 2 true places and 2 false places. Two places where it's not negated and one where they are. Okay. So if there's assignment, I can match all boys and girls. Okay? And if matching of all boys and girls, there's an assignment. Okay, so that's what I want to argue. And so why can I do this? It's because, well, what I do is I take my assignment and, I take my assignment, I just argued this, right? If I take my assignment, what I do is I configure the gadgets corresponding to each one of these things to choose either the vertical or the horizontal configuration, the true or the false configuration. And now, for any clause, I know if there's one of these variables, one of these literals that is true, one of these pets is available. Okay? If for example, the Y gadget is set to false, I know that the Y, the odd pets are free. They're not matched. So I can use them to match this boy and girl, and they are now happy. Okay? So that says every clause has a pet. Now, if a matching of all boys and girls, there's an assignment, and it's just the same argument. This is very tight. It's tight both directions, right? If I do have a matching of all the boys and girls here, there's some pet that was free in some gadget. That means that gadget was set to true or false. Okay, it's very. I mean, this gadget is a little complicated, but once you construct it, it's clear that they're exactly the same thing. Okay, so now you have some pets who are lonely, so you don't want that, so it's just sad, so you go add some boys and girls to pick up the remaining pets. So you can see the whole construction here. These are the clause boys and girls, right? This is, let's say that I'm hoping this is a clause for this clause. So what I should do is one of these is going to correspond to the odd pets. Right? It's going to match the odd pets here, P3 of x, an odd pet. For x bar, for y, it's going to be an even pet that this triple is going to allow this boy and girl to use or to take as a pet. And the z is a not, so it's going to be the odd pets that are free for this boy and girl to use. Okay, that's the clause for this one. This is the clause for one of the other ones, and that's the clause for the other one. Okay? And you can see there's a 3D matching here because it's satisfiable. That's the 3D matching. What I do is I assign, what does this thing correspond to? Assigning x to what? Assigning x to false, right? Vertical is false. Okay. And no, assigning x to true. Which one was this? Let's see. Right. Assigning x to true. Right. And so the assignment here is x is true, y is true, and z is false. Does that satisfy this? X is true, y is true satisfies this. This is satisfied. Z is false, this satisfies this. So it's a satisfying assignment. And you can see that everybody has pets. Okay, and then there's the lonely pets who either go away or you can match them using just adding boys and girls to match all the extra pets. Okay? Does that make sense? Okay. Oh yeah. Okay, so now I'm moving to this other one, and I should give you this for the. Should I give you a break now, or it's a little early for a break? Okay. Let's just go. Okay, we can look at this. Okay, I guess you're supposed to be quiet, but I was meant for this to happen after the break. But what is this? What am I illustrating? I'm illustrating branch and bound, or backtrack search, right? It's the. Okay, so I don't know. Do you like Woo? I don't know. We don't need to vote. NP completeness is everywhere. It's the church Turing thesis. The Turing thesis is that everything's a computer. The whole world is a computer. That's essentially what Turing said. Is that you can't do many things. Back when they discovered undecidability, there's like, once you make a problem complicated enough and you can allocate storage, then you can't figure out much about it. That's what Turing said. And then In NP completeness, there's a search problem where we go ahead and suppose the solution is easy to check. And here, still, it's sort of universal. The computation is sort of models everything. Okay? The world is polytime, is what we're saying, is our computation. And somehow the world solves these problems, and somehow it's if it's a problem in the world, it somehow must solve it, because otherwise it'd be undecidable or NP complete, and it would have problems solving it. Okay? Okay, so on the other hand, we see problems right and left and center that are not solvable. So what do we do? Okay. So one thing we can do is exponential search, which is, I mean, in some sense, what this says is the world is not solving things optimally, right? I mean, it's no right? I mean, an elephant's a big thing, but it has problems, right? It's not perfect. There's no perfect being out there. Well, maybe bacteria. I don't know. But the bacteria are only good until the fungus come and get them, and then it's all, it's not clear there's any optimality in the world, right? So we're trying to go for optimal solutions, and this philosophy is maybe just doesn't apply to the world. Okay. So intelligent exponential search is backtracking and branch and bound. In some cases, it seems to be working. It works in practice. There's a lot of excitement in the EE side of, and not just the EE side, not EOR, of solving integer programs like with millions of variables. It's a little shocking. You may want to use that in your project solutions. Somehow they work in practice, and I'll show you what they are. You can get somewhat close to optimal. This is what I worked on for research, and that's proving that this algorithm gets within a certain bound of optimal, and we'll talk about that. We've already seen it in greedy for set cover. We didn't find, that was the one problem for which we did not find the optimal solution, and there's a reason for that. Why do you think we didn't find the optimal solution? I already didn't give you an algorithm for it. It's NP complete. Right? And not only is it NP complete, in fact, you can't do better than a logarithmic approximation. So it's really hard to approximate better than what we showed you. So that is the best algorithm for it, which is shocking. Okay, so in heuristics. This is what you're going to do for your projects. Okay. Okay, so backtracking. Okay, so backtracking is, there's some pseudocode, and the pseudocode is a little annoying. Okay, so I find this annoying, but say you start with a problem. So what's the problem? For now, picture a SAT formula. Okay, that's the problem. You're given the problem. Okay? Now with the SAT formula, if I set one of the variables to be true, okay, this is a set of active subproblems. Choose a subproblem, remove it from our set of active problems. So initially there's just one formula, okay? And I expand it into smaller subproblems. Okay, so now with the SAT formula, how might you do this? How might you take a formula and do something with it and now say, okay, if I can solve either this one or this one, then I can solve the original one. It's fairly clear, yeah. Yeah, that's simple. You should all just immediately picture that. And we'll, in fact, picture it on the next slide. It's a chicken or egg problem here. But, right? Does that make sense? You can, if you want a concrete example with the pseudocode, you can think of P0 as the original formula. When you choose a subproblem from P, it's one of the formulas you have, which in the beginning is the original formula. You expand it into subproblems, P1 and P2. You pick one variable, you decide whether that variable, you make a problem where that variable is set to true, right? And when you set it to true, what happens to the formula? Any clause with that variable in it, which is true, you just delete. Where it's not negated, any clause where it's negated, you just remove that variable, okay? Because you set it to true, and therefore not x if it's x, not x is false, which means one of the other two variables better be true. So you just remove it. And so you have two problems that look very similar to the original problem. And then for each one of the PIs, you see if you're done, if you already have a solution, which in the SAT formula would be an empty formula. Okay? Or it would be an X and an X bar. Right? If you have an X and an X bar, then that would also tell you it's false. Test a PI fails, you discard the problem. Otherwise, add PI to S. So there can be, you could either say you're done by saying yes, it's a solution, or you're done saying no, this is a proof that this problem can't be finished, and then you add it to S. Okay, and then finally you announce there is no solution. Okay, so here you announce the solution. This is the case where you actually found one. If you run out of problems, if you run out of subproblems, you stop and say you're done. Okay, if your Q ever goes to 0. Okay, so here's an example. Okay, the initial formula is phi. Let's set W to be true. Now, if you set W to be true, what happens to now we look at all the clauses with W in them. Okay, so now all the clauses with W in them, for these blue clauses, what does it do to them? We set W to be true. We just can cross them out. For these red clauses, what do we need to happen? And you see what the problem is going to be down this branch? Already you can see what the problem is down this branch. So this is so that what you do is you get a new formula, and these first two are missing, and the last two have Z and Z bar. You just cross out the W bar. If W is false, then it's switched. You keep the last two here are good, so you just throw them out, you satisfied them. The first two, you just cross out the W's. Okay? So the first two clauses here are the first two clauses in the original formula with W crossed out. Now we're going to go to continue, X is true, and so on. We have, again, the slides do step by step show you colors and show you the colors are there for a reason. I don't often refer to them, but I should, right? The blue means that those clauses are good, and the red means you have trouble. Now, can you satisfy this clause? You have to make this clause true. You have to have a literal in it that's true. There's no literal in it, so it can't be true. Okay? Okay, X is false. And then you get a different one, and so on. Right? You get these sort of things which can't be solved. Okay? Do you see the idea here? I guess this is not satisfiable. Or, yeah, it looks like it's not satisfiable. Okay? This is backtrack search. Okay? So it's called backtracking. You don't see it so much because this particular thing, yeah, it went in this direction, and then what it did is it went up there and came down here. That's what it happens. Really, the implementation is just some queue, right? You have a list of problems you can expand. Here, this problem, and this problem is in your list. It's a frontier, okay? Just like breadth first search through this space of problems. Okay, any questions? Okay, so now there's some choices you can make. Which subproblem to expand? Which variable to expand? Perhaps subproblems, you know, one heuristic. Which one heuristic is you use a subproblem with the smallest clause and then choose the smallest clause and then choose some variable in that clause. Okay? Because that's going to get you to the contradiction fastest. Right? If you remove all the variables from a clause, you know that whole path is dead. So you've eliminated that. Okay, what you need for each subproblem, you need a quick test for, is this a fail? And we saw that in the previous slide, that an empty clause is a fail. That whole, you don't need to continue enumerating variables along this path. Okay, is it a success? If it is a success, all the clauses are gone. Right, that's the success test. And then there's the maybe where you just add it to your list of problems and you continue exploring. Okay. Okay, so now I'm going to give you a break. Okay, so we're back. Okay, so now, well, now maybe you can understand my, see, that's backtrack search, right? Okay. Did it backtrack? It did it backtrack? I don't know. Yeah, I'm backtracking. That's hilarious. I don't know whether it's hilarious, but it's exactly like one of my jokes, which is, I'm sorry. I apologize that you have to bear that burden. I'm making fun of myself, but okay. Okay, the best solution. And in fact, it's more than that. There's actually heuristics for lots of things. Even inside of backtrack search, these SAT solvers, they do various things to say what a promising path is. So this thing I'm going to tell you later is also good for, I mean, in TSP or these problems like TSP, you want to find the best tour. You want to find the tour that minimizes the cost. And there you might get a handle from the cost of the tour you've done so far, right? So, so you know, now you have more structure. In fact, even in real life, there's structure even in this formula. You can do some heuristic in the formulas, in a partial formula, to say this one looks more promising, more than just the number of variables. You can use number of variables, the size of the thing, so you can use a priority queue on your problems to sort of choose what you explore. And that's what we're going to do. Well, essentially, we're going to take the generic algorithm is going to be essentially the same as backtrack search, except we're going to use a priority queue to choose what problem to explore more, or what partial solution to extend, right? The partial solutions in the assignment is we've assigned variables to some of the variables, true and false. Okay, so so again, you start with the partial solution, and again, this is a generic algorithm. You let S equals one problem, the set of active subproblems. The best so far is infinity. We're assuming we're trying to solve a min problem, a minimization problem here. So the best so far isn't very good because infinity is very large. And you repeat while S is non-empty. You choose a subproblem or partial solution P in the S, remove it from it. Extend P, you extend the solution, and you may be able to extend it in several ways. Again, it's like you could use true or false or add a city in TSP for each problem. If PI is a complete solution, if it's a complete tour, or if you assigned all the variables, you can report whether it worked or not. Or here, in case you could just compute the value of your solution. Else if, now we're going to add this thing called lower bound. If the lower bound, we're going to add this function that gives you some more power to sort of guide your search. Okay, the lower bound is something you compute about the solution, which is maybe good. And then if it's best so far, then if it's less than best so far, you add PI to S. Okay, and then return the best so far. And now you can choose the subproblem partial solution based on some estimate here, this lower bound on the solution. Okay, so there might be some partial solution that you can prove you don't extend, right? For example, in the assignment, we found an empty clause before assigning all the variables. We haven't assigned all the variables, but we can still say this is not going to work. Okay, that's sort of a lower bound. Okay, that's intuition with the finding a solution as a part of the better. Okay, again, which subproblems to explore next, and then you should use a priority queue. You have an access. You've thought about the problem, and you thought about it in a way that tells you, well, okay, this doesn't look good. And not only that I can prove that it has value at least so much. Okay, and I'm going to show you that. Okay, for optimization problems, start with some partial solution. It's also sometimes called A star. Let S the set of active partial solutions, best so far, repeat, extract partial solution with the lowest lower bound. It's exactly the same thing as before. Okay, and then you extend the solution to the rest, and it's all the same, right? This is, all I'm saying is you put the, you order which ones to explore by which ones are the most promising. Okay. Okay, here's a solution. Say I have some, what's a partial solution for the TSP? What's the TSP problem? It's a, do you know the TSP problem? Oh, who knows the TSP problem? Oh, he talked about it. Okay. No, okay. So should I tell you what it is? Okay. Well, you just have a map with a set of cities. Do I have it? Yeah, it's, this is the TSP. You have some set of objects. You have distances, cities, and you have distances between them, and you want to find the tour that minimizes the cost. And the problem comes from back in the day when you had traveling salesmen, and usually, I guess that's why they named it. Like in mathematics, the reason I say man when normally I use gender neutral or both is because that's the name of the problem. I don't know. It's all, you can get in trouble or not. I don't know. But so you have n cities and you want to find, a tour means just an ordering of the cities, right? That's all it is. It's just an ordering of the cities. Which one, and you can start at V1, it doesn't matter, because you're going to come back to V1. Okay? Does that make sense? Okay, so now let's go back. So the partial solution is just the cities that you've decided to visit so far. Okay, so where you start is the first solution, and then you may extend it to any of the other cities. Okay, so at some point you have some set of cities, a partial solution, which ones have you already got to, how do you get to the rest, and then come back. Okay, or what order do you visit the rest of the cities? Okay, so there's this subset of the cities. What's a lower bound? What's a lower bound on the cost? And now here we're going to assume everything is positive. All the weights are positive. The distances are positive. One thing you can do is you notice that a tour, if you think of it as a graph, it's a cycle. It's some sort of cycle. Okay, and in some sense, it also is a cycle. It spans all the nodes, right? It spans all the nodes. It's a connected graph that connects all the nodes to each other. What's the minimum cost way to connect all the nodes to each other? The MST, right? So the tour is something that connects all the cities together, and we want to find in a certain way, but it has additional requirements. It has to be a cycle, okay? The minimum spanning tree does some of what the tour does. It connects all the cities together, and it is the minimum value thing. So it's very related. There's something very related about it. And moreover, it's a little cheaper. We know for sure it's no more expensive than the tour, right? The tour has one extra edge for sure, and also it may just do something completely different because it has to do a cycle. But they're kind of related. So, what I just argued is that the tour cost is greater than or equal to the MST cost. So you take the cities, you view it as a graph, you take the distances between all pairs to be the weights on the graph, and you take the MST of that. Yeah?
Quick question, in this case, wouldn't the tour cost be strictly greater than MST cost? Because the tour would have to be a cycle, rather than the MST has to be a tree.
Yeah, I mean, yeah. It has to be greater than or equal to. But I mean, it doesn't, the or equal to doesn't need to be there. Yeah.
Okay.
Yeah, fair enough. Okay, so, well, I mean, unless there's zero cost edges, but yeah. Lower bound on partial solutions. Okay, so now if you visit, now I want to do this lower bound thing. I want to do this fancy thing that I was saying you could have, lower bound. Like, how do we have a meaningful lower bound? Something that tells us so right now, even before we've explored anything, the MST is a lower bound. Costs no more than the MST. I mean, costs more than the MST. So it's also true that if you've already visited a lot of them, and you collapse those nodes into one, and then take the MST of the remaining graph, that's a lower bound, and now you sum the cost. Okay? The cost so far the cost of visiting those first k, plus the cost of the MST for the rest of it is a lower bound on the whole solution, on any future solution. So this is a little bit cool, right? You're not just using the cost as a lower bound. You could say the cost so far is a lower bound, right? How much did you pay already? But we can also say that we can use MST as a lower bound on the future cost. Any solution extending from this is the cost of what I've incurred so far, plus the MST cost of getting to everybody else. Okay? Now, it's not the correct answer. It's just a lower bound. Okay? We know we're going to pay at least this much. We might pay much more. We might pay just that. Okay? So here's a, okay, does anybody see the tour here? Does anybody see the tour? No, you can't see the tour because it's NP complete. That was a funny joke. Okay, so, okay, so. Okay, this is going to be, it's not that exciting of a, it's exciting to me, but, oh, look at this. Okay, this is basically exactly what I described. Can you guys see it? You want the font lock mode off? It's good? Okay. It's doing what I said. Popping this pop task is, it's pulling stuff off the list of problems. It's adding stuff to the list of problems somewhere. It maps maps the extending thing. So this is generic. There's a lower bound of whatever the problem is. It's just generic. And of course, because we did all this, A star, you pass in, it's a higher order functions, right? The TSP lower bound, when you're done, how to expand, and the original problem. So that's just what A star does, right? It is that generic procedure, and I filled it in with the TSP lower bound and the TSP lower bound. Does something, it looks at the path, it computes the cost of the path here, and then it does something and does something and does something. I forget what that all is. But the claim at the end is that it's the MST cost of the collapsed graph and the path cost, which is what I claim. Okay? So that's one of the procedures. You need to say when you're done and blah, 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 right? And here's when you expand. You expand when you add you add somebody who you've not, all the possible things you can add to your tour. Okay, that's what it's doing there. It does something with, yeah, these maps and stuff are all impossible to understand after you wrote the code a year ago, so, or 5 years ago. So, okay. So let's see what happens. Okay, I have the wrong version of Python. Okay, so blah, 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 but it's only a warning, so I don't really care. So here's first of all, I did a little bitty graph, because I couldn't understand what was happening with my broken code. So this is the original graph. It has 4 nodes, so you can see it try to work. There's the problems, the new problems that are generated from the first problem. And it's doing that, eventually gets a solution, right? Okay, very exciting. Okay, so, and now it does the problem, this other graph is the problem we saw. It's this pictured thing. It's the same, I tried to do the same graph that's on the slides. And you can see that doing it. And then you can see that the total number of nodes explored is 21, okay? So now let's do something really stupid. Okay, so now it's not a very interesting lower bound. 0 is a lower bound. Okay. And you can see, So 21 is the number of subproblems the tree, the total nodes you explored in the tree. So I hope it's more. It is more. Okay, it's 112 nodes that are explored with the stupid lower bound. With more clever lower bounds, you can probably get away with less. It's a very small example. A factor of 5 is meaningless, but 112 is meaningless. If you take the same example and multiply by 50 and you get 5 to the 50, and that's meaningful in terms of improvement, right? So that's why these lower bounds in engineering, these lower bounds are what you will be suffering with on your project. We had a big discussion about your project before it went out. I'm very scared of the project because it has unbounded costs to you. So don't spend too much time. That's all I'm saying. It's fine, okay? We tried to make it so that it'll be reasonable. If you just type check everything, you should get 3 points, okay? Out of 5, all right? So not 3 out of 100, that would be brutal. But yeah, so, and the other things, you know, I'm pushing for more points, but we'll see. But just learn the material, okay? Okay, so this is the tour. Okay, great. Okay, so now let's look at approximation algorithms. Okay, so given an instance of say you have a problem, and you're given an instance, and the cost of that solution is B. Okay, and you want to find, it's a minimization problem. So there is a solution with cost B. Okay? Say you find a solution of cost at most alpha times B, at most alpha times B. You build an algorithm that you can prove works and always produces solutions whose cost is less than alpha times B. Okay? The approximation factor for that algorithm is alpha. Okay? If alpha is larger or smaller than 1, for which one? So this is just, do you understand? Is alpha larger or smaller than 1? Yeah, it should be larger. If it's less than 1, it's nonsense, right? It says there's a better solution than the optimal solution. Okay? Just to get oriented. So you could define it for max. It's the same idea. Here is beta larger or smaller than 1 for max. You have an algorithm, you're trying to maximize something, maximum matching. And you have another algorithm, or maximum 3D matching. Maximum matching we know we can do, right? But maximum 3D matching is NP complete. So what's the best approximation? I have an approximation algorithm that does 10 times the best. Does that make any sense? No. Okay, so it has to be less than 1. I get 2/3 of what the best is. Okay? So which I think is actually the best algorithm for 3D matching. But, okay. Now, the question is, have you seen an approximation algorithm? Well, I told you a long time ago that you have. Greedy set cover. So the solution of size O of k log n, this is a minimization problem. You're trying to find the minimum number of sets to cover your underlying universe or your underlying set of elements. And we said, just greedy, the greedy algorithm, provably always, right? It doesn't say that for some solutions it can't do better. Okay, that's not what approximation algorithm means. Some solutions, some problems, it may just give you the right answer. Okay, but what we're saying, what an approximation algorithm is you prove every instance you're going to do well, at least this well. I don't know whether this is well or not, but this is what we can prove. And this is an O of log n factor approximation algorithm. Okay? Okay. So now I'm going to give you an approximation algorithm for TSP. Okay, so there with greedy, with set cover, it was just using greedy. Okay, let me actually review the idea here in set cover. What was the idea here? How did we know we made progress in set cover? Yeah. Right. Every time we cover at least 1 over k of the remaining elements. And we're really using, why do we know that? Because we knew there's a solution out there of size k. We thought about it, and we said, look, there's a solution, it's of size k. And then we're like, so why are you telling me this? I don't know. Oh, look, there's a solution of size k. Listen to me. There's a solution of size k. So that tells us there must be one set that covers 1 over k of the remaining elements at all times. Okay? We really thought about the structure of the solution, or at least the size of the solution. And then we inferred something about the structure of the sets, right? That there is a set that covers 1 over k of the remaining elements. Okay? So we used this fact, k. We thought about what sets mean, and then we said, look, there's one set that covers 1 over k of the things. That's going to give us some progress, and we can calculate that progress. Okay? Yeah. Okay. I've been obsessing why everybody can't be everybody can't be below average. I've been obsessing about that, and I'll talk to you about that later if we have time. Yeah, it's weird to be obsessed by that, but okay. So I think it's interesting. Okay, so you're giving a TSP instance, and now we're going to give a special type of TSP instance. We're going to get one where the triangle inequality works. Okay, so the triangle inequality, it's this formula, but it says, you know, if you want to go from I to j, you can go from I to k and then from k to j. That's fine. Right? Because you will end up at j, so that's fine. And the cost is the cost from I to, at most, the cost from I to k and k to j. There might be a better way to go. Directly, there might be another way to go. But going through k is totally fine. And your cost is no more than going through any other place. That's the triangle inequality. Okay? So another one of the criticisms is that I should write on the board more, but I don't write on the board. I decided, yeah, okay, that's actually very fair. Except I don't like writing on the board because you have to watch me write on the board. So, but here, all this triangle inequality says is that and also it's because it's a failure. I should have put it in the slide. Okay, this distance, oh yeah, that's why I don't write on the, okay, let's see where it goes. Nice. Maybe a triangle, okay. This is k. It says this distance here is less than this distance plus this distance. It's the triangle inequality. One side of the triangle is less than the sum of the other two sides, right? Okay. So next, I should have put that in the slide. I will next time. Okay, so now here's a way to get an approximation. Okay, I'm going to get within a factor of 2 of the best tour. And what I'm going to do is find the minimum spanning tree. Now I have a tree, like I just look at the tree and I was like, okay, I can walk around on the tree. Let me just walk through the tree. Okay? How do you do a tree traversal? Whenever you do a tree traversal, do you go like depth first search or breadth first search? It doesn't matter. Well, depth first search. Let's do depth first search. And then you go down until you get to the leaf and then you come back. Right? How many times do you cross each edge when you do that? Twice. Have you reached every city? So that is a tour, right? It's not necessarily a tour because you visit this node a lot of times when you do this, right? You go down, that's the leaves, you go back up, and then you go down, and then you go back up. So, in fact, what we do is, this is not a tour because you keep going to the same city over and over again. So but we shortcut it. You see, this is a triangle. It says this red edge is less than going from here to here. Okay? So you can shortcut it. So that you may get better if you do that. You may not be better. It may be just the same. Okay? So this is an approximation algorithm. Okay? It's guaranteed no matter what TSP instance you give me, as long as it obeys the triangle inequality, is this is an algorithm. All you do is you make a minimum spanning tree, you write down some tree traversal of it, and you splice out the repeats using this algorithm. You shortcut. If you see repeated vertices, you go to the first one that's not repeated and put in that cost. Okay? So that's guaranteed to give you the right answer. I mean, it's guaranteed to give you an answer within a factor of 2 of the torque, no matter what the instance is. It's not always that bad. It can do better. It can never do worse. Okay? Okay. And why is, first of all, the cost is at most twice the MST, and we knew before the tour is at least the cost of the minimum spanning tree. So this is thought, again, this is the same kind of thought you needed to put into the backtracking search. It's like, what is the structure of the problem? Can I say something about the structure of the problem? If I can say something about the structure of the problem, perhaps I can prove something. Not maybe get the optimal, but get something close in this case. Not maybe for the branch and bound, not prove that it makes the algorithm go in less than exponential time, but at least maybe make it go faster. Okay, so this is a factor of 2 approximation. Okay, the best known is 1.5. It's called Christofides algorithm. A famous Turing Award conjectured that the answer, after seeing this algorithm and seeing how simple it is and blah, 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 and how central these problems, linked these problems are, thought there was a factor of 2 approximation was the best possible. The next year somebody did better. So yeah, so you can, this is very nice. The algorithm here is you just do an MST, and then remember Euler? Who remembers Euler from 70? Who loves Euler from 70? Okay, I love Euler because it's like Hotel California. Okay, so that's the proof. Okay, so there's if the graph is even degree, we know we can go on we can cross every edge once, right? Does that remember that in Euler's theorem? So all we do is we take the odd degree vertices and we compute the min-cost matching, and that gives you an even degree graph that gives you a tour, and the matching's cost is at most half the tour. So that's the algorithm. Okay, vertex cover. Okay, we want to find the smallest set of nodes that touch every edge. Okay. Okay. So it's called cover because for each vertex, each edge is covered. One of its endpoints is in the cover. Okay? Does that make sense? Okay. Yeah, let's just draw it, I guess. We'll draw some approximation. Okay, that's the node here. Okay, so there's a good vertex cover, which is you take the center node, that's of size 1. Or you could take these nodes all on the outside, that's of size 5. You're trying to find the minimum, so which one's better? The one in the center, right? So you can imagine what might be the best, what might be a reasonable heuristic. Pick the vertex with largest degree, okay? Is that also, right? That's the largest degree? Okay, we know what that does. We know already that's a pretty good algorithm. We can prove a bound on that. We know that's O of log n from the set cover algorithm, right? Okay, because if there's a k more vertices that cover the rest of your graph, then at least one of them must have n over k, the remaining number of nodes over k, the remaining number of edges over k neighbors. Okay? So here you could actually just reduce this problem to set cover. Okay, the elements are edges, that's what you're trying to cover, and the nodes are sets. All the adjacent edges that are being covered. So you can actually just translate it. And when you translate it, the largest set and the largest remaining degree are the same algorithm. Okay. So it's a min number of sets to cover the elements. Okay, can we do better? So do you think you can do better? I probably wouldn't have shown you this if we couldn't do better, right? Okay. So let's do something that looks stupid. Let's take an edge. I don't know, do you see edges here? I see one. Let's take that one, the blue one. What? Oh, the other ones are going off to the rest infinity of the graph. Okay? So these edges are going off and it's connected in some C of graph. That's my picture. That's the imagery you should be having. Okay. Okay, so, sorry. Okay, so you take one of these edges. Now I'm going to do something weird. To cover this edge, I'm not just going to cover it, I'm going to cover it. I'm going to put both endpoints in the set, both of them. Okay, now this edge is like, dude, man, I got covered by 2. Okay, but that's fine. I'm going to do that. Okay. I'm going to remove that, but I cover some other edges. I don't even care how many other edges I'm covering. I'm just picking any edge, putting both endpoints in the cover in my proposed solution. Now I'm going to remove all the incident edges. Let's see if so this is the cover. I'm just leaving it there, but I've covered all these other edges too, right? All these edges that go off to the infinity of the rest of the graph. Okay, so I remove them, and now I pick another edge, which is, this one is available. I haven't removed it. And I put both of those endpoints in the cover, and I keep going. Okay. So now look at this. Look at these 2 edges. They don't share endpoints. Right? There's something nice about these edges. If I've anybody who is covered by this guy, is not neighboring these. Right? These edges are disjoint. The set of edges in M. Share no endpoints. And now, okay, so I did 2 things here. I put the edge in this thing called M. M. I don't know, what does M mean? And then I put both endpoints in my cover S. So I'm building sort of 2 objects here. M, and I'm building S. Okay? The set of edges in M share no endpoints. So why did I call it M? Because it's a matching. Right? It's a matching. The M I'm building is a matching. Okay? Right? That's what a matching is. It's a set of edges where no two edges touch the same vertex. Right? Because when I did this remove, I made it so I couldn't put any of these edges that I removed in the matching. I removed all the things that could have shared an endpoint with this blue edge. I removed those edges. So they're not going to be put in M. Okay? So now any cover must include at least one endpoint of an edge in M. Now if you look at the set in M, it's a set of edges. And I have to cover all the edges. Right? So this tells me that at least one of this, I mean maybe I was being kind of weird to put both endpoints in, but I know that any optimal solution for this left blue edge here, I sort of save the left blue edge for the people watching on video, so they don't, because they can't see the laser pointer. But this left blue edge here, at least one of these endpoints has to be in any vertex cover. And that's true for this one. At least one of these 2 endpoints has to be in any vertex cover. So any cover must have size bigger than the size of this matching. Okay? So any matching, so stepping back a bit, it says any matching in this graph is a lower bound on the size of the vertex cover. Just like the MST was a lower bound on the size of the TSP, tour. Okay? Okay, so this says any cover must have the size, at least the size of M. Okay, and what is the size of my cover? Well, S has 2 vertices for each edge in M. So our cover has size 2 times M. Okay? So it says that our solution has size 2 times M. Any solution has to be at least M. So it says we're within a factor of 2 of optimal. Right? And this happens over and over again, right? We're saying we're using the notion of the structure of optimal. What does optimal have to do? In the set cover example, optimal had to cover all the elements. So therefore, there must be one set that covers a lot of them. Okay? In this one, optimal had to cover all these edges. Okay, and these edges, I can find a solution that's only twice the cost of these edges. What did the TSP tour do? It connected all the cities. Oh, the MST connects all the cities. So the TSP tour is at least the cost of the MST. So for approximation, you need to show a lower bound. You need to show optimality. And you saw this before already you see, this matching is crucial, but you saw it already in duality, in linear programming and duality, right? You know you're optimal if you have a dual solution. And that's very powerful. And it's actually very powerful in linear programming algorithms as well. Okay? So, I think I have to let you go. I'll see you on Tuesday. Thursday.